Hi, welcome to the pre-calculus lecture series. And in this video, and I'm very excited we start a new chapter, chapter 4. And this is a very important chapter, the two functions we're going to talk about in these videos. Well, in this chapter will be the exponential functions and the logarithm function. Both functions plays a very, very important role in the calculus. Okay, so we're going to spend a few sections to talk about each of the functions here. Okay, so let's go ahead to start the section 4.1. We're going to do an introduction about the exponential functions here. Okay, so let me go to our lecture notes and let's get started. Okay, so the first is here, just like always, when we start, let's start to introduce what is the exponential functions looks like. So the way we define the exponential function is f of x. This is, we call this the ax here. Okay, so in here, the a has to be greater than zeros here. Okay, and a cannot be equal to 1. Yeah, so if you see it's 1, it will just be constant, right? 1 to the x power will be the constant. So here, be careful, right? So the key things here, a is greater than 0. And this a here, we call the a here, this is we call this the base for the exponential functions. And because of x is on the exponent, right? So this is the exponent of the a, so that's why we call this is exponential functions. So the base can have like many different base, like some useful bases here, like the one you typically see, that will be like the base of the 2, right? So if the base is 2, where is the application we use? We use, like all the computers, right? So the computer coding and like the hardware, and it is based on the base of the 2 for the computer programming. And then also like we have what's called is a special natural exponential. So this e values, right? So this e is 2.7128. I think we learned that before. So those are probably the most useful. And then the other ones here is a base 10s here, right? So base 10s is the typical we use for in our number systems here. So those 3 probably are the most useful ones here. So that's what we call it is the exponential function. So first, let's take a look. What is the exponential functions looks like? Okay. So we know the exponential function, right? So this is f of x equal to a to the x here. So let's take a look. We have like 2 kinds of so we know the a. So we know the a has to be greater than 0, right? So in here, so this exponential functions here, so we have one like this, right? So for this exponential function, a is greater than 1. So it's a kind of intuitively truth, right? So when the x getting greater and greater, then because this is greater than 1, so that's why it's going to go to the infinities, right? Then when the x become, when x become negatives, right? So the a to the negative power is 1 over a, so still the positives here, right? So this is the situations like we call this, when the a greater than 1. So for examples here, so if you have so for example, if you have like a function like 2 to the, the 2 to the x powers, right? So that's what is the 1. So according to this ones here, the few things we need to notice here. So the domain here, okay, domain for the exponential function, the x's belong to the whole real numbers, okay? And what is the ranges here? The range is here is because this x-axis will be the asymptote for these functions, right? So the range is here, the y has to be greater than 0, okay? So then we know they have the horizontal asymptote is what? Is the x-axis is here. Then one of the key point is this point. This one's here is what point here? This is the ones, right? Because why this is 1? This is a to the what? 0 powers, right? So z to a to the 0 power, that's why it's 1. So we have another type of the exponential function is this is the one, okay? So this is x and y here. And then the function is go like this way here. Right, so the function go like this way. So this is the situations that a is less than 1. So for examples here, right? So if you have some functions 1/2 to the x here, so it's kind of like true when the x get bigger and bigger, this whole number going to get smaller and smaller, right? Because it's 1/2 to the power, getting very small. Then when the x equal to the negative, because the x equal to negative, for example, like x equal to -5, if you put it here, then the 1/2 is 2 to the -1s, right? To the -5. What happens here is 2 to the 5th, right? So that's why it's go this way, it's getting bigger, right? So here, okay, so in here for this type of the functions here, the domain still is what? The x here is what? X belong to the old real number. So in here, the range is the same. The y has to be what? Greater than 0, right? Because this number is the asymptote. So we still have the horizontal asymptote at where x equal to is the x-axis here, right? Or you can say it's y equal to 0, right? It's the x-axis, y equal to 0 is the asymptote. The same way, so here is the key point, right? So one of the key points here, this is 1. So it's the same thing, it's a to the 0 power, right? It's 1. Okay, so that's what is our basic exponential function. So like in here, right? So for a here, if the a getting bigger, all right? So if the a getting bigger, and then the way your function going to get steeper. What I mean is here, so if this is my other functions, I'm still going to go through 1. So if this is like, so for example, if this is a1x, if this is a2x here, so what happens here? That means A2 has to be greater than A1. It's go a lot faster. That's why, special, for today's we have a pandemic, we call that this is exponential growth, right? So that's why it's going extremely fast. So the same ways, for here, right? So like in here, because this is the functions here, right? So if you have like another functions here, like another one is go way steeper, right? So this is way steeper. So if this is A2 and this is A1, right? So this is A1. Be careful here, right? Because A2 is the, is the like less than 1. So that means this one go a lot faster. That means they decrease a lot faster. So for these situations here, A2 going to be less than A1 here. Okay, so we make sure, you understand why this is 1, right? Because this is a potentially, it's exponential decrease a lot faster. This is exponential increase a lot faster here. Okay, so now the first thing is here, let's take a look. And how do I get the value of the exponential? So of course in here, typical you use your calculator. I think the calculator, you should have a key, something like this. Like it's kind of like the hat here. So like if you said 3, so typical you say 3, then you put it here, then you put whatever, like this is 5, right? You said 3 over 5 here, right? So the 3 to the 5th power. So try it and to see, you'll be able to use your calculator. So the value I input into the calculator here, this is 243. And this ones here is just like the same way you put it like a 3, then you do a hat, and then you do a negative 2/3. Okay, so I will get the number. This is 0.48075. And so this ones here is the same way, just 3 then to the what? To the pi's, right? So this will be 31.544. So this one's here is 4.72 AA. So make sure, try to get familiar with your calculator because it probably will be very helpful. And when you try to, later use it to find the value. So use those values to see you'll be able to duplicate my value or not. So now you know how to operate your calculators, right? Okay, let's take a look at the problem number 2. Let's say find the exponential function ax with given the graphs here, right? So what's that means here? Okay, so that means, right, 2 and 25, that means x equal to 2, y, or the y is equal to 25, or y, you can say is f of x equal to 25, right? Okay, so now let's plug in there. So when the x equal to 2, y equal to 25, so I will say 25, right, equal to a to the what? Square. So I take the square root, so a is equal to 5, or the a is equal to the negative 5. By our definitions, I know the base cannot be negatives, right? So the base is 5. So now I find my functions here. So I know my function f of x is equal to 5 to the what? 5 to the x, right? So this will be my exponential function. Okay, so now let's take a look. This one's here, 3 and 1/8. So the same ways, right? So it's the same ways here. What that means here? The first one is what is x, and the second one is what is y. Y is f of x here. Okay, so now let's try to solve it. So it's 1/8, right? Is equal to the a/3. So in order to, solve these problems here, because this is what? This is the third powers, right? So if I can change these ones here, so the 1/8 is to what? It's 1/2 what? To the what? To the third power is equal to a to the 3. So now you see, you change both of them have the third power, right? Third exponent. You can just remove that. So you know the a is equal to what? 1/2, right? So the a equal to 1/2. So that's what happened. So your f of x function is what? Is 1/2. So the exponential x. See here, that's why it's going down. So this one we call this type of the function, we call it is the exponential. The decrease, or we say decay. Okay, so we said a decay. And this situation we typically call it is exponential growth. Okay. Okay, so now let's take a look at the next ones here. They said, hey, try to graph this based on my parent, like the function 2x here. Okay. So now let's take a look at the 2x here. So just like we said, let's try to make this is a little bigger. So this is 1, 2. So 1, 2, 3, 4, 5, 6, 7, 8. All right. So here this is 1, 2, 3, 4, 5. So we can see better. Okay. So the 2x. So let's make a table about the 2x here. okay? So this is x, this is the 2x. So we know the key, right, will be 0. 0, what is here? I have 1, right? So I have this point, 0 and 1 I have here. Okay, so now I have the next ones here. I have x equal to 1. So what is here? Is 2, right? So I have x equal to 1, y equal to what? Equal to 2. I have the next ones here. Or, okay, so now 1, 2, 3, okay. Okay, oh, that's why it's too high. That's what I was wondering. It's 2's here, right? Okay, so it's 2's here. Okay. Okay, so now let's try one more. So I said 2. So this is will be what? It's a 4, right? So let me try to graph it's 2. This is a 4, so it's here. Okay, so now let's do the other side. So other side I say is -1. So that will be 2 to the -1, right? So what is here? 1/2, right? So I know this one's here, 1 is 1/2 is here. Okay, and then the next one's here, I have -2. So this will give you -2 to the -2 is 1/4, right? Okay, so let's see here. So this is 1/4. 2 is very small. So this is my what? This is my parent functions here, right? Okay, so now they say the g is 1 plus. So what does that mean again? It's adding up, right? So this point go up here, this point go up here, this point go up here. So the same way this point go up here, and this point go up where? Go up to the here a little bit here, right? Okay, so in here we need to be careful because it's 1 plus 1s, right? So this is a plus 1s here. Oh boy. Okay, so because this one is a plus 1, so the same way I need to move my what? I need to move my horizontal asymptote 1. Okay, so because this is a plus 1, so here, let me see, be careful, this one should be a little bit above, right? So a little bit above here, right? So the same way, so you don't forget, you need to move your asymptote 1. So let me see here. Okay, so this is your asymptote, horizontal asymptote, you need to move up 1 as well. Okay, so now what is my final graph? My final graph will go like this. Okay, so because then this line I'm going to touch the here, right? That's the asymptote. Okay, so now let's do the part of the next ones here. So let's also mark my point, my key point, right? So like we said, when we do those type of problems, we always mark the key points here. Okay, so it's 1, 2, 3, 4. Okay, so this is 1, 2. Okay, so in here we say the key point here is 1, 1 is 2, 2 is 4. All right, then the -1 is 1/2, -2 is 1/4. So this one is this is my parent function. And now, do you remember what is this ones here? That means it's flip, right? So flip to what? Flip to the x-axis, right? So this point flip over to here, this point flipped over to here, then this point flip over to here. Then this point flip to here, this point flip to here. So now my final graph here will be like this, all right? Okay, so now this one, okay? So this one's here, very interesting here. So this is a 2 x minus 1's here. Let's try to do my basic graph first. Let's mark it. Okay, so I'm still using red to represent my parent function. So it's that 1, 1, and 2, 2 and 4, 1/2, a quarter. Okay, so this is my right? So this is my graph here. Okay, so now what does this mean? That means this is x minus 1. So that means what? I move to what? I move to right. How many units? 1 unit, right? Okay, let's take a look. How do I move it? So this point move to here. This point move to here. This point move to here, right? Then this point move to here. Then this point move to here. Okay, so now you still have the same asymptote. So here, this is my graph, right? So it's very basic and for the graph here. Okay, so now, and the first things here, we're going to say, okay, this is the exponential and the power graphs here. So I want to, so here, the reason why we want to compare the power functions. So, right, so the power functions here will be like, for examples here, if you are comparing 2 to the x or x to the square, right? So in general, we are comparing, the a to the x and the x to the a's, right? So be careful about the those notation. This is x's exponents, right? So this is what we call it as exponential function. Okay, and this one's here, the x is on the bottom, the x is on the base, and the a is the power. So this one's here, we call it the power functions, right? It's a power function, or is kind of like a similar like the polynomial, like here, like x squares, right? So in general, here, ax and x and a's here. So when the x getting big, okay, then the ax is here going to be greater than xa. That means ax is going to be running a lot faster, going up a lot faster. Of course, like in the beginning, so sometimes xa is bigger, sometimes ax is bigger. But if you try to graph it, okay, so you try to graph it, so in here, so in the beginnings here, right? So in the beginning, we don't know. Sometimes maybe sometimes it's growing, depending on what is. But in here, so this is xa. So after a while, when the x getting bigger, the exponential is going to go a lot faster. The reason why this is an important concept is because when you go to the calculus, right? So this is very useful in the calculus. When you go to the calculus, about the limit. So when I try to find the limits of the function, it will be very useful. So they will tell you, like the ax is running faster than the power, believe it or not, we're running faster than the logarithm function, the one we're going to talk about next. Okay, so one of the things in the exponential functions very, very useful is how, we typically use the exponential function to talk about the compounding interest here. So what is a compound interest mean? That means if you deposit money, so for example, if you deposit $100 here, right? And now if they give you 10% interest, so like after 1 year, 10%, right, you will have the 110. So the second year, the way they calculate the interest, they add these ones here, and then they give you another 10%, right? So that will be, another 10% will be 11, right? So in the year, right? So it will be 11. So in the year 2, you will have 121. Okay, so that means you include the interest as the principal again, right? So like if this is a 10% interest, right? This is after 1 year, you will get 110, right? Because 10% of the $100 is $10, right? So this is $10. So now your new principal is 110. So from this new year, they're going to use the 110 as your new principal. Then they give you another 10%, so it's $11, right? So that will be your new principal. Then if you continue, so like in here, they will give you another 10%, it's 12.1, right? So it's 12.1, you will get 133.1 on the first year, second year, third year. At the end of the third year, you get 131. This is what we call this, the compound interest. You put the interest back to your principal and then let it grow. So most, in the most of the bank today, they all use the compound interest, right? So compound interest depends on how do you compound it, right? So you can say, hey, I compound every year. Or then said here, hey, I can compound every half year, every month. That means you calculate the monthly, how much, then you add back. The more you compound, the more interest you get, right? So the more frequencies you compound, the more interest. So the more interest you get. Okay, so that means, if I have $100, I can compound daily, weekly, monthly, quarterly, or semi-annually. Even, of course, my interest rate will change. It depends on how frequently you compound, right? So if it's 10% for annual interest, and then if you compound semi-annually, then you use 5% for every 6 months when you compound, right? So now here, this is the important formula. So this is the value of the amount you're going to get after the certain period will be P plus 1 over, this is R to the N, and this is NTs here. So a few very important things. P's, this is your initial principal. That means how much you input initially, all right? And then the other ones here are, this is very important, this is, we call it is the annual interest rate. This is annual, right? This is annual interest rate. So divided by N, what is N here, right? So N is equal to numbers of compounding in a year. So for example, so for examples here, if you compound quarterly, so that means every quarter you're going to calculate the interest. Now what is your N here? Hey, N is 4. That's reasonable, right? So because your R is your annual interest rate. Now you want to do quarterly. So of course you need to find out what is the interest rate for a quarter, right? So you divide it by 4. Now what is this numbers here? The NTs here, right? Okay, so here the T is equal to the numbers of year, right? Okay, so because in here you're compounding quarterly. So if I say 2 years, so how many quarters here? It's the N times 2, so it's 8 quarters here. So that's why you need to change to whatever the frequencies you want to compound, right? So for examples here, right? So let's say here, okay, so for example, so you need to, these two has to match, all right? Okay, so for examples here, if the T is, let's say it's 5 years, right? And if you want to compound monthly, okay, if you compound monthly, so what is the N here? So N is 12. So you need to use your annual interest rate divided by 12 to get your monthly rate, right? Then total how many months you have? It will be the 12 times 5. So you're going to get 60 months, right? So this is your NTs here, right? Be very careful here, right? So this is one of the most, most commonly applications for the exponential function. Okay, so now let's see here the problems here. Let's say find the annual percentage yield for investment that's earn an interest rate at 6% per year. Okay, and then the 6% per year. Wow, compound what? Daily. Okay, so they want to find the annual percentage yield, right? Annual percentage yield. Okay, so 1 year, right? 1 year, right? Annual percentage yield. Okay, based on my formulas here, so my R is what? It's 0.06, right? So what is my N's here? So my N's here is what? My N's here is 365 days, correct? Okay, so based on my formula, so my amount after 1 year will be what? Will be the P 1 plus what? 1 plus 0.06 divided by what? Divided by 0.365, right? Because you're compounding, right? You're compounding dailies, right? So 375. And for 1 year, how much you have here? You have 365 days, right? So remember, as long as those match is here, that will work, right? Okay, and now in here, you see here, now see here, if you simplify this, this will be P. If you put this into your calculator, the whole distance here, into your calculator, you will get this is P, what? P times 1.06183. Okay, so your percent yield, right? So what is the percent yield here, right? So that means those are the extra you gains, right? So percentage yield, right? So because the P was your original, so the 0.06183, that is the percentage yield, right? So I know the annual percentage yield based on my compounding daily is what? It's 0.06183. So this will be 6183%. Okay, so it's pretty easy application. So the problem can ask you is like they can ask you different things. They say, hey, after 5 years, if I want to achieve this amount, right? So with a certain, like for example, the 6% every year, if I put into a bank, the bank will compounding like quarterly. So if after 5 years, I want to get $5,000, how much I need to input here, then that's why you can put it into the formula and find your principles, right? So that's how do you, kind of use this information. So yeah, so this one here is a very useful application and important formulas, right? So make sure, we know this, and for our next lecture, we're going to talk about several other very useful exponential application. We call it the exponential decay and exponential growth. See here. And I think that's it for this sections. This is a pretty brief sections and a short section, just an introduction about the exponential function. So key things to remember, exponential function is a lot, growth rate is a lot faster than the power functions, right? And also the key things is this graphs here, right? So the horizontal, asymptote, domain, and the range is here, right? Okay, that's it. And nice to talk to you. Have a good day. Okay, bye-bye.